Welcome back. Today is November the 16th, and hopefully we can finish chapter 10. All right. The last time when we met, we were going over problem F, and we saw that it was a ring opening of an epoxide. And so let's continue here. So, what do we have here? We have a we have the addition of acid to a secondary alcohol. So what kind of reaction type is that? If I just add an acid to an alcohol, but this is not a dehydrating acid. So what kind of reaction is this?
Is it SN2 borderline?
It's just SN2.
Okay.
Yeah. Let me see. No. This reaction is an SN1. Sorry. Yeah. Check this out. You add acid to the OH. The OH gets protonated into water. It leaves, and then you make a secondary carbocation. You keep this chiral center. Then you have one hydride shift. And that's gonna give you another secondary carbocation right here. Then you have another hydride shift. From where? From here to here. And then you get this tertiary carbocation, right? So now your iodine will has the potential to produce how many products now? 6. So your iodine can go up and down there. So you will make, these are your choices. Up and down. Down and up, iodine here. And then 2 more for this one and 2 more for that one. This reaction is very useless because it produces too many products. So this is up, this is down, iodine, this will be up, this iodine will be up. This reaction is very inefficient. And finally, the star carbocation. This one stays up, this one down, plus both up. So that's what you will get here. Terrible reaction. But nonetheless, good for teaching. All right, so these two came from the tertiary. and this would be your major product. And since it's SN1, you get SNR. Likewise on the other two. All right. Next reaction. What kind of reaction is this? This is not protection of alcohol. This is not a tosyl chloride. This is an acid. This is an acid that we're adding now. So it's an organic acid. So this OH grabs the H, forms water, water leaves, and now you have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. You have a carbocation here. This is a secondary carbocation. What type of reaction is this? Is SN1. Oh no, it's not gonna be SN1. It's going to be an E1. Why do I know it's E1 here with so little? Okay. It's E1 because your tosylate, it's a, so this plus water was formed. This is a poor nucleophile. It's really bulky, so it's going to deprotonate. So your chances to deprotonation are here, or one of these H's. So if it grabs this H, or if it grabs this H, it will give you different products. How many products can you form? Let's see. If I grab the proton with the red root, I'll get this. This is my Hoffman product. And if I get the proton with the green root, how many products I can make there? 2. So I'll make the trans, or E, and I will also make, if I can make the trans, I will definitely make the cis. So this will be my major product in the whole thing, and these two are side shift products. All right. PBr3 converts an alcohol into a bromine, an alkyl bromide, and this OH is up, so it'll turn it. It will flip the configuration as in down or dash. So this metal will be up, this isopropyl will be down, and this OH now it turns into a down Br. So this is a pure SN2 reaction. All right, the next reaction is ring opening of an epoxide under acidic conditions. The base is the O, grabs the H from this acid, and now you form this intermediate that is elongated like that. This methyl is towards us, and the H is towards the back. Now my nucleophile, the alcohol, is going to lose 1 hydrogen by the conjugate base, the acid. So its options are 1 or 2. Where would they attack? Carbon 1 or carbon 2?
Okay. Would it be the one with the less substituents?
No, that happens for basic.
Okay.
This,
Then would it be one?
it will be 1, yes. Thank you. So it'll come and attack here on 1. And it's going to, so every time you see this, remember this is partially plus, and the oxygen is plus, so there's repulsion there. So this is the bond that is going to break, with these 2 electrons are going to be transferred to the oxygen. And now you've made, do the anti-periplanar thing, show it like that. The OH will go on the top. The new group minus a hydrogen will go here, methoxy, and then this methyl will be up but wedge, and the hydrogen will be towards the back and dash. All right, so what kind of reaction is this? Ring opening of an epoxide. Also, is it SN2 or SN2 borderline?
Would be borderline.
Exactly, SN2 borderline. Very.
Right, or I could get it out.
Oh, that's you, Kaylee. Good morning.
Good morning.
All right. Hey, at least you're awake. You probably awake since 5 or something, right?
Yeah, 4:30.
4:30, my lord. I used to do that at the beginning of the semester. Now I'm back to my normal, waking up at like 6:30. Yeah, so SN2 borderline because we are under acidic conditions here. All right, we got a couple more. So what does it look like to you? SN2 or SN1 here? This is definitely going to be a substitution. And one hint, this is a primary alcohol. If you protonate this, it's going to form a primary leaving group water. And this
Will
water,
it be SN1?
it will be SN2. Because the bromine is a very good nucleophile, so it'll look like this. So first it protonates, and now the bromine is kicked off, and he's back with a vengeance. And it goes. So it'll form that. How I know it's not SN1? Well, it's not secondary or tertiary, so it cannot be SN1. So rule that out. And then, so all those little things you have to consider. That's what makes this subject kind of hard to deal and master. All right, one more for this page, and we're gonna go to one more interesting page. So this is a protection of an alcohol. So it simply, this is not an SN1 or SN2. This simply is a substitution reaction where you're gonna substitute that H with a tosyl group. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 carbons, and my tosyl group is the N. All right. Lots and lots of stuff to practice. So go ahead and practice some of these problems again. Take the blank PDF that I uploaded on Canvas and try to do them by yourself again after you've seen it. That helps. All right, let's do short synthesis. So this is the most difficult thing in OCHEM, honestly. Thinking backwards or thinking forward to finish something. So it says propose a synthesis from the starting material given to the final target. There might be several possible answers that are correct. And usually when I give this homework, I ask my student to see if the answer is acceptable, because I used to have a friend from Hong Kong who used to do karate, and he used to say, "There are too many ways to skin a cat." So, meaning there's too many ways of doing something, like poor little kitties. You don't want to skin them, but that was his saying, and it always stuck with me for years. I still think about that phrase. So anyway, let's take a look at what's happening here. So I see that this part of the molecule has not changed. And then I have an OH that turned into this is a thiol group, an SH. So somewhere along the line here, I need to turn this OH into a good leaving group and nucleophile it with sodium SH, and I have to do it in an SN2 fashion so that I can invert the configuration. All right. So this is what I can envision from this reaction right off the bat. So I want you to start thinking backwards. So if I put this like this is a retrosynthetic analysis arrow. It's one with two lines, and it's empty. Those two lines are empty. And the arrow is always pointing towards the starting materials, representing that this is a backward thinking. So if a common intermediate here would be, okay, I'm going to have a good leaving group in place of the OH here. And so any good leaving group, how can you turn an OH into a good leaving group?
Make it a water.
You could do it. Water will give you, that's a good idea. Water will give you an alkene, though. It'll be elimination. It'll be an SN1, and you're going to end up with either a double bond here or a double bond here. So you have to be careful with that. Or you might end up on an SN1 with the OH up and down here. So that's careful. I wouldn't do that. So just tosyl group. A tosyl group will do. So check this out. Going forward now. So this one, I can easily make that from there. So notice that I put like the level of difficulty goes from private to captain here. Sometimes I mix it all the way to general. With chiral centers, big molecules, yeah. So, this will do. So now, thinking forward, I know that I can go from here to here with thionyl, no, not thionyl, tosyl chloride in pyridine. So here's where your awesome memory comes to play: the remembrance of the reagents. Now, this is a paper test, so you're very lucky because I have to do most of the stuff for you electronically. But next semester, we'll have paper tests, and you have to show me your work here, which is kind of cool too, because you can be creative, and we're not also limited to right or wrong with the electronic grading. So you'll get partial credits. So sodium SH DMSO, that will be my idea here, and this will be a SN2 reaction with a polar aprotic solvent. Yeah, so I will solve that like that. How about the next reaction? Let's take a look what is new. So I start with an alkyne. So you remember your alkyne reactions. So right now I have, besides the benzene ring, I have 2 carbons, 1 and 2. So I have one, this will be this carbon and this carbon. So I need to add 2 more carbons. So this is new. All right, like here, this was new. This was the new part. All right. So I need to add a 2 carbon chain somewhere. Now, check this out. Thinking backwards, what would be the common intermediate between these 2 molecules? I have a triple bond, and I have added a 2 carbon chain there. So some of my students have told me that sometimes they cannot think backward entirely. So they do a little bit forward and a little bit backward, and they meet in the middle. I think that's a really cool strategy too, that as a student I would definitely use it, because you want to try to come up with the answer. So the common intermediate here will be this guy. Triple bond, just like the one on the left side, and then an ethyl group. Now you can see here on the final product that you can do a tautomerization, right? And from starting material to the middle, you can do an alkylation, right? All right, so I think we got this. So let's alkylate this. What would be the conditions for the reaction? 1, you will give me what? Sodium amide deprotonates this H, and then you add ethyl bromide. That will put that piece right there. And then going forward from here to here, check that out. What would you do? I hope you haven't forgotten this. Hydrolysis of an alkyne. You remember this? Water and sulfuric acid, and in the presence of mercury sulfate, that gives you that. So that will put the OH here, the H here, the OH in the most substituted carbon. So you will have an intermediate that is the enol, like that, and then that rearranges to the ketone. Did you remember that? I think you do. But at 8:26 in the morning is gonna pull it through, right? Or pull it out from the brain. I understand. All right, you guys. Are you guys more awakening now? It's 8:26. Let's go. Check this next example. What is new on this example? Now I have so this whole thing, all these carbon skeletons are here. My main core. Now notice that I have a double bond, and I had to manipulate it so that I reduce it completely, and then I form an alcohol. Now, if the answer was the OH here, oh, that's easy, right? You just add water and sulfuric acid, you do a hydrolysis. But it's not that simple. You had to, so basically you had to go from a double bond here to a double bond here, and then insert the OH group. All right, this is how I will envision it. Now this is a Sargent reaction, so it has a little more steps. So I will say I'll go from here. I'm going to migrate, so I can envision an elimination prior to this to make an alcohol, to make that alkene. So my intermediate towards the right. Notice I have 7-member ring here, so I will, let me do this in black. I'll have a double bond here and a methyl group there. Going towards the left. Now I envision that I can make that alkene from an alcohol that is here, right? Doesn't matter if it's up or down at this point, we're gonna get rid of it. So racemic works. And then this is easy. That takes me to starting material. All right, going forward. All right, so how would you get, what would you do here? This is hydrolysis of an alkene. Boom, you make that. Not a hydrolysis, hydration, my bad. We're hydrating. We're not destroying. Hydration of an alkene. From here to here, what would you add? Help me out. Think of something. How will you get rid of that alkene and that alcohol? Make an alkene. That's dehydration, right? So your choices will be that you have seen POCl3 in pyridine, or an easier one. How would you dehydrate an alcohol? Concentrated phosphoric acid or concentrated sulfuric acid gives you that. All right, this one I won't help. How will you make that? How can you put the OH in the least substituted carbon now? Anybody?
Hydroboration.
My man, who was that?
Elijah Heron.
All right, Elijah. Excellent. Hydroboration will get you there. So, BH3 THF and hydrogen peroxide in sodium hydroxide or potassium hydroxide, either one. All right, that's how you will do that. All right, check this out. The level of difficulty is increasing. So I can see that this group is right there. So this is new. The OH there is new. And I forgot to say that this was new. All right. So how do we put an OH there that is adjacent to another OH? Think about it. What would be the common intermediate for this? How can I put this new OH in a carbon that is next to a carbon that has an OH? Anybody? All right, how about a ring opening of an epoxide? Check this thing out. Here I will have my carbon skeleton in my epoxide there. If I want to, well, here I have to put the OH in the most substituted carbon, but both of them are substituted equally because this molecule is symmetrical. Going from here to there, I'm simply add acid in water. That will protonate this OH, and then the water will come from the top and add there. And then more water grabs the excess hydrogen that is in there, and that will pop this up. All right, so that's how you would do this reaction. All right, let's go backwards. All right, how do I get to here from this? I still need to work with that. How can I make an epoxide starting from this thing that I have? So here it will be hard for some of my students. This next intermediate is crucial. So I still keep my carbon skeleton. 2, 4. Put my OH here. And I will have a halohydrin form here to make that. So when I only add sodium hydride, this scheme is I think it's on, what chapter was that? Chapter 6, I think. And this is like the first time how halohydrins were used to make epoxides or oxiranes, and you do it that way. And so a halohydrin comes from what? An alkene. So I have my 1, 2, 3, 4 carbons in a double bond, and I can finish this reaction. Going forward, go from here to here with a reduction. With an elimination. So POCl3 in pyridine. Now you have this reaction that you can use. Or you can use concentrated phosphoric or concentrated sulfuric acid, either one. Going from here to here is halohydrin, and you use bromine in water. All right, and you finish this synthesis. All right, so we're doing well in time. How about the next reaction? This is a little more complicated. This will make you think on a test. But I have students that have solved it, so it's not the end of the world. You just need to see what's happening here. So notice that this skeleton remains. Hold on, let me do that in green to be consistent. Like this was the skeleton for that other one. So that's the skeleton. I see it here. So how can I preserve? Notice I'm gonna make a chiral center. A chiral center where I'm keeping my methyl group down and putting a methoxide group. That is not a joke. That's kind of hard to do. And then for my bromine turned into a carboxylic acid. So in your head, you have to say, oh, that bromine, I had to turn it into an alcohol somehow. And then I have to oxidize the alcohol to make the ketone. You see that? All right. This is the key. This is the start. So what I will do, if I was you, I said, here we go. This carboxylic acid, which is new. This is new, and this is new. Let me do that in green. These two are my new things. How do I put that in there? And that's how you solve these things. Say, okay, the previous step must have been an alcohol. So I keep this the same. This CH3, this is CH, this is a CH3. It's just, you have to do computerize it backwards like that. But that's what that is. And then this group will never change. The chicken leg isopropyl group. And here you will have an OH. So I don't know if the OH will be up or down. In my head, I know it will be down because I know this group is up. And notice whenever you have an oxygen and another oxygen next to each other, that comes from an epoxide. This guy right here will come from an epoxide. So I can say with confidence that this came ring opening epoxide of that alcohol. So I'm gonna go a little bit more backwards. And I'll do this. That will look like this. Can you envision that now? All right, let's solve some of these. So from here to here, I use what? PCC. This is an oxidation reaction. Not bad. From here to here, this is a ring opening of an epoxide. Do I do it basic or acidic conditions? As in SN2 or SN2 borderline? And what will be the ingredients that I need? All right, acidic, because I need to flip the methyl group down. So I will add methanol in the presence of an acid. Sulfuric acid is a good one. So this reaction will be an SN2 border. All right. So we're almost there. Going more backwards. What's the precursor of an epoxide? An alkene. Notice that all these reactions, whenever you might want to manipulate an OH, like we did over here, we moved where? Right here. We manipulated this OH and we start with an alkene. The intermediate was that alkene. So every time you want to make an alcohol, it has to go through an alkene. And the same thing if you want to make an epoxide. The common intermediate of an epoxide is an alkene. So here you will have that. Here you will lose your chiral center, but this chiral carbon, when you do the epoxide, will guide the oxygen on the epoxidation down, because this part here will be blocked. The top part will be blocked. Going forward, if you use MCPBA, This will be an epoxidation. The epoxide will be preferably formed dash or down. Oxidation, and finally you have done from here to there. Going forward, what would you need here? This is a pure A2 reaction. I'm not doing elimination. What would I use? I would use something like sodium methoxide in the presence of an alcohol under heat, and I'll get that form. So this will be my side safe product. All right, we got 6 minutes and a little bit. Where is the last slide? Oh, there it is. Oxidations and reductions. So I want to show you some things that you need to know for oxidations. This is called Jones reagents when you have H2 dichromate, dihydrogen dichromate. Check this out. Here you have two tertiaries and one primary alcohol. I'm sorry. You have one tertiary, this is a tertiary alcohol, this is a secondary, and this is a primary alcohol. Which alcohols will get oxidized? 1 or 2 or 3?
Three.
Huh?
3.
3 will not get oxidized. It doesn't have an extra hydrogen here on the carbon holding the oxygen. So 3 is safe from harm. So the secondary turns into a ketone, and the primary turns into what? An aldehyde or a carboxylic acid? Carboxylic acid. So H2 dichromate can oxidize primaries and secondary alcohols, but not tertiary. All right, how about that? Potassium permanganate in heat and OH. Here you have a primary, this is a primary alcohol, and this is a secondary alcohol. All right. Will it oxidize to both? Yes. To what? The primary turns into what? Notice that you have 1, 2, 3, 4, 5 carbons on the chain. So I'll go 1, 2, 3, 4, 5 carbons on the chain. My primary will be turned all the way to carboxylic acid, and the secondary turns into a ketone. So potassium permanganate can oxidize primary alcohols to carboxylic acid and secondary alcohols to ketones. All right, we got 3 minutes and 3 reactions to do. Okay, lithium aluminum hydride. I'm just gonna give you the answers here. Lithium aluminum hydride will reduce anything that has a carbonyl, all right, but not the double bond. So you have 1, 2, 3, 4, 5, 6, 7, 8 carbons here. So you go 2, 3, 4, 5, 6, 7, 8. This OH, this carbonyl will turn into an OH, and this one's too, OH, and the double bond will stay intact. So lithium aluminum hydride can reduce aldehydes, ketones, and carboxylic acids, but does not reduce double bonds. All right, next, sodium borohydride. Check out sodium borohydrides. I'm gonna write it down. Can reduce aldehydes, ketones, and hydrides, and acid and acyl chlorides. But it cannot reduce carboxylic acids or double bond. All right, so here you have the same skeleton 8. 1, 2, 3, 4, 5, 6, 7, 8. It'll reduce the aldehyde. It will reduce the ketone, but the carboxylic acid will stay the same and the double bond. And finally, reduction. Hydrogen in platinum or palladium or nickel can reduce ketones and alkenes, double bonds, but does not reduce carboxylic acids. Okay, so here you will have 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. The aldehyde, ketones, aldehydes, I forgot aldehydes, and double bonds. So it will reduce that, but it cannot reduce the carboxylic acid. The double bond also will be reduced. All right, we finish this chapter. Have a wonderful day, guys. Let me stop the recording.